Greetings once again from Rescue Shuttle Control. We're showing on our telemetry that you've made great progress in controlling your onboard lighting system, and that's very good. We've also noticed, however, that it's having some impact on your power supplies. And so as you are controlling the lights, our next priority is going to be to show you how you can recharge your batteries and get your solar systems up and working. So with that in mind, today's session will be exploring some new techniques and some new methods. And among the new things that we'll be learning today will be about a new component called a photoresistor. We'll also be learning a little bit more about our hero and a new way of getting information from it. This will be the serial monitor. And in addition, we will also be exploring how the hero can provide us with not just digital high and low information, but how we can communicate with it with analog information. So those will be some of the new ideas and the new techniques that we'll be exploring today. And so let's jump right in and see what we can learn. I think we'll start first off by talking about this thing called the serial monitor. Up to now, we've basically been communicating with the hero through inputs and outputs of a digital nature through pins on the hero. That's fine, but we might like to send information a little bit more rapidly and a little bit more efficiently than we can by simply blinking lights on and off. Fortunately, the hero includes something called a serial port, and we have an ability to control that and to communicate through it. You'll notice, if we switch our attention over to our coding window, that we have in the upper right-hand corner a little icon that when we hover over it says Serial Monitor. If we click on Serial Monitor, a new window appears right here. And this window will show us text information that is sent to us through the serial port from the hero. And we can control what information that is through commands that we write in our code. You'll notice that in our code block up above here, so far we haven't added anything except a single line in the setup routine, which is serial.begin with an argument of 9600. What this means is that when your code begins to execute and setup is run at the beginning, serial.begin will open up the serial communication line. And the 9600 is just an indication of how fast that information will be sent. In this case, 9600 means that it will be sending us information at a rate of 9600 bits per second, or 9600 baud. That's not the same thing as 9600 characters per second, because it may take 8 or 10 bits in order to send a single digit or a single alphanumeric character. But it gives you some idea of the speed with which we are going to be sending information. And 9600 is a pretty standard baud rate to use. So that's what we'll use in this set of examples. Now, we should explore a little bit about what this allows us to do. And so in order to do that, before I define any variables or write any really functioning code, I'm going to put some test code into the hero and see what I can observe on the output of the serial monitor. So let's go ahead and paste some sample code in here in the loop part. So you'll notice that what I've placed in here, as indicated by the comment, is a command serial.print, and serial.printin is going to simply print out the message, "Hello, Earthling." It will wait for half a second and then print another sentence, "Take me to your leader," and then wait for another 1,000 microseconds or 1,000 milliseconds or 1 second, and then repeat as long as loop is executing. The thing to keep in mind here is that since we are sending this at a very rapid rate, at basically thousands of characters per second, I wouldn't really be able to see the screen changing because it would be changing so fast unless I paused and placed these delays into the code. So that's the only reason for putting those delays in. Let's go ahead, upload this code, and see what happens as we watch the serial monitor down below. So we upload the code, wait for a few seconds, done uploading, and here we go. So we're now getting communication through the serial monitor. And you can see just as we requested it to, it's printing, "Hello Earthling, take me to your leader," interspersed with pauses. All right. So that's very helpful, at least in terms of being able to understand how the serial monitor might work. But what's really going to be useful to us is to send in, data that we're interested in through this function. So in order to get into that subject, I think the next thing we want to do is start talking about the idea of analog information. Let's go ahead and turn off the serial output here just so that it won't be distracting us too much. So we'll go ahead and take care of that. Done uploading. Okay, we'll clear the output on our serial screen. All right. So the next thing that I'm going to do is I'm going to introduce some variables at the beginning of our code block. And I'm going to introduce 3 variables. Won't use all of them immediately, but we will eventually use all of them as we're working on today's project. The first of these is a variable called sensor pin, which might seem pretty familiar to you because we've used sensor pins to provide both input and output to the hero before. You'll notice, however, that we're using a sort of an unusual pin number this time. Usually we were using pin numbers like maybe 12 or 11, something like that. Now we're using sensor pin A0. And if you look at the hero, if we reach over here and have a look at the hero, you'll notice that there are a series of pins in the lower left-hand corner that are labeled as analog in, with numbers like A0, A1, A2, and so on. These are the pins that we're now using. The distinction between these pins and the ones that we've been using before are that these are aware of and sensitive to a range of voltages, not just 0 volts or 5 volts, not just low or high. As a matter of fact, when we send a voltage, an analog voltage between 0 and 5 volts to one of these analog input pins, the result will be a number that can be in a continuous range between 0 and 1024. And so that will give us the ability to measure a more or less continuous range of values and not just on and off. That's the main and important distinction between analog and digital functions. So you'll see how that'll be useful to us today to be able to measure a voltage in a continuous range. The other 2 variables that we've defined here, which we'll be making use of in the not distant future, are another LED identification, onboard LED, which is defined as number 13, will allow us to turn on and off an LED that's built into the hero. It's this one that's glowing right here, right now. And so we'll use that instead of what we've been doing in the past, which is to activate an external LED mounted on our breadboard. Finally, we'll have a variable here called sensor value. Right now it's initialized to a value of 0, but eventually sensor value will be holding the results of measurement that the hero performs when we ask it to. So that sort of sets the table for us a little bit. The next thing that we want to do is talk a little bit about this new discrete component that's called a photoresistor. As its name suggests, it's a resistor, not too different from the ordinary resistors that we've seen before, like the one that's mounted here on the breadboard. But what's different about a photoresistor is it doesn't have a fixed value of resistance like this 220 ohm resistor does. It has a resistance that depends on the amount of light that's falling on it. So this particular photoresistor has a very high resistance when it's in the dark, when there's no light falling on it. It might be actually many thousands of ohms of resistance, or even millions of ohms of resistance in total darkness. However, when light is falling on it, it conducts electricity and has a smaller resistance. In this particular case, when light falls on this photoresistor with an intensity that's equivalent to Earth sunlight, its resistance drops to only a couple hundred ohms. Very similar, in fact, to the resistance of our 220 ohm resistor that we have on the breadboard here. So what you can see is that we'll have different amount of voltage drop across the photoresistor depending upon whether its resistance is much smaller than, much greater than, or comparable to the 220 ohm resistor that it's connected in series with. To explain that a little bit more clearly, let me just point out to you what we have currently set up on our breadboard. We have our 5-volt source connected through this red wire that connects to one lead of the photoresistor. After passing through the photoresistor, we then connect to the 220 ohm resistor, and then finally, through this blue line, return back to ground to form a closed circuit. So depending upon what the value of the resistance is of both the fixed resistor and the photoresistor are, some amount of current will flow through this circuit. Now, let's imagine for a moment that we're shining enough light on the photoresistor that it has a resistance of 220 ohms, just the same as the fixed resistor that comes next in the circuit. That would mean that of the total 5-volt drop from 5 to ground, half of that would appear across the leads of the photoresistor, and the other half would appear across the fixed resistor. So 2.5 volts, and then 2.5 volts and down to ground. On the other hand, if the photoresistor, say, was in extremely bright light, so that the resistance of it was negligible, then that would mean that essentially all of the 5 volts would be occurring or dropping across the fixed resistor. So the voltage that we would observe on the top side of the fixed resistor would now be 5 volts instead of 2.5. And now I hope you can understand what the opposite would be. Suppose we were to put the photoresistor into darkness. If we put the photoresistor into darkness, it would have an extremely high resistance. And so that means that essentially all of the 5 volts would appear as a drop across the photoresistor, and there would be essentially 0 volts drop from the top of the fixed resistor down to ground. So what you can see now is that if we were to probe the voltage at the node between the photoresistor and the fixed resistor, as its voltage is either high or low, it tells us whether the resistance of the photoresistor is low or high. That is, it tells us whether there's a bright light shining on it or not. So we're going to make use of that. Just to give you a little indication now of how we might use some of this new information that we've just learned, let's go ahead and put some code into our loop. What I'm going to do is replace our Hello Earthling code with something a little bit more useful. So let's go ahead and paste that in and talk a little bit about what it does. So you'll see from the comment here that what we're now doing is we're going to read a value from the analog sensor. The analog sensor in this case is the voltage on the bottom end of our photoresistor. And we're going to send the results of that measurement, to the serial monitor. So we have here first an assignment that occurs. Sensor value is going to be changed from its starting value of 0 to whatever is read on sensor pin. And sensor pin, you'll remember, was A0, analog 0. So whatever value occurs there, if, for example, it was 2.5 volts, halfway between 0 and 5 volts, we'd expect to see a value come out here of about half of 1024, something around 500, 512. On the other hand, if the light is very low and the voltage there is very low, then we'll see something closer to 0. So this is basically what we're expecting to see. So let's do a little test on it first by connecting sensor pin to some voltages that we know what they are, and we'll see what is shown when serial print of sensor value is performed. So let's go ahead first of all and upload this code. So uploading. And we're done. All right, so now what you can see is a series of zeros that are appearing in our serial window. And the reason why zeros are appearing is right now I have analog sensor pin A0 connected to ground. So let's take this orange wire and let's connect it to some different voltages. If I were to connect it to, say, the 5 volt that's coming in at the high side of the photoresistor, I should expect to see a number corresponding to the high voltage. And sure enough, there we have 1023 appearing, which is basically the top value corresponding to plus 5 volts. If I instead connect analog 0 to ground, as it was when I started, so I'll put it over here on ground, you can see that we go down to 0. What we want to do, though, is measure the voltage between ground and the point that's between the photoresistor and our fixed resistor. So I've got a point here on the breadboard that allows me to do that. And sure enough, you can see we get an intermediate value. Right now we're getting a value of 64. So that's 64 out of 1024. And that tells us how high the voltage is at that point relative to the maximum of 5 volts. Now you might be wondering, well, how do I know that this is corresponding to the light that's falling on the sensor? Well, I can do some experiments. For example, I can take a flashlight and I can shine it on the photoresistor. As I shine a flashlight on the photoresistor, I see the counts, that is the value, rise up to 400 and more. So that tells me that I am indeed measuring light input. I could also do the opposite. I can take a cover and place a cover over the sensor to place it in darkness. When I do that, you can see I drop down to a value very close to 0. Not quite exactly 0, but it's not perfectly dark in there. So I've accomplished part of what I wanted to accomplish so far. That is, I've succeeded in getting the hero to accept analog information, that is the voltage output by my photoresistor circuit. And I've also succeeded in transferring that information through the serial monitor in a numerical form that could be used by me or used by someone who needed that information. So that's not the last of what we want to accomplish today, although that is fairly important. The next thing that we want to do is add an additional feature to our circuit. You'll remember that a few minutes ago we talked about having an additional variable that we defined here that identified the onboard or the built-in LED light on the Hero. That's number 13. We can now use some logic, use some code within our loop function to not only send information about the brightness of the light that's falling on our sensor to the serial monitor, we can also use that to flash an LED on and off and give us an immediate visual indicator of the state of, say, charge or discharge of our batteries as they are being charged by solar panels. The next thing we'll do is insert code for the Hero to execute that will actually use the information coming in on the sensor and then use that not only to print information out on the serial line, but will also control the blinking of the lights on the onboard LEDs on the Hero. Now, in order to do that, we have to now make use of the onboard LED ID number. You'll notice up here that we've identified onboard LED as 13. And so we can't forget that we have to now make pin number 13, in other words, the onboard LED, we need to make that into an output. So once at the beginning of our run, we're going to need to go to Setup and insert the pin mode command as we've done before. So let's go ahead and add that to our setup code right here. All right, we now have pin mode. Onboard LED is an output as we need it. Okay, now we need to modify the code in the loop function. So not only are we going to basically send information to the serial port, but we also need to control the built-in LED. So let's go ahead and replace the code that we have here with the modified code. Let's examine it a moment and see what it's doing. The comment tells us that we're going to pulse the built-in LED not for a fixed time now, but for a time that's determined by the results of the sensor output. And so you can see that the first thing that we do here is that we measure using analog read the value of the voltage on the sensor pin. That'll be translated into a number between 0 and 1023. Sensor value now is the variable that holds that result. And we'll use that to call digital write on the onboard LED. So we'll call digital write, turn it on, and then wait for a delay equal to sensor value. So if the light is bright, the LED will stay on for a long time. And if the light is dim, it'll be on for a smaller number of milliseconds. Then we call digital write to turn the LED off. Once again, wait for sensor value, and then we would repeat this over and over again. Of course, before we repeat in the loop, we'll execute the code that we had before, which is to send through serial port using the function print line the sensor value, and then wait a little bit, and then return to the top of the loop. Okay, so with that code complete, we should have everything that we need. So we'll go ahead, we'll upload the code, and see how it performs. Uploading now. Uploading is complete, and we are getting numbers coming through on the serial monitor as we expected. Sort of comparable to the light level numbers that we were seeing before. I should be able to increase those numbers by shining a flashlight on the photoresistor, and indeed, just as before, we get a higher number with the flashlight on, we get a lower number with the flashlight off. But now we have an added indicator. We can see here that the onboard LED corresponding to output 13 is now flashing at a rate that's determined by the light falling on the photoresistor. And so you'll notice that when I shine the flashlight on the photoresistor, the blinking is now slow. In other words, it's on and off for a long time. And when I remove the flashlight, it goes back to blinking more rapidly. That is, on and off for a shorter period of time. And as before, I could cover up the sensor, and I should expect to see the blinking become much more rapid. As a matter of fact, as I cover the light up more and more, the blinking becomes so rapid that eventually I can't even detect it flashing on and off anymore, because it's basically going on and off too rapidly to see. But when I let the light back on the sensor, I see it blinking again. So we have succeeded in what we set out to do here. We've learned about how to use the serial monitor. We've also learned about how to use analog inputs into the Hero. We'll build on this knowledge next time as we try to add additional logic to our code that will be relevant to our problem at hand, which is monitoring the state of charge of our system on the shuttle. And so until next time, please remember, build everything and be safe.